On March 11, 2011, at 2:46 p.m. local time, the Fukushima Daiichi nuclear power plant in Okuma, Japan, operated within normal parameters. 6 boiling water reactors maintained stable temperatures and pressures. Emergency systems remained in standby mode. Seismic detectors registered baseline readings. The facility functioned exactly as engineers had designed it to function in one of the world's most earthquake-prone regions. Within hours, 3 reactor cores would experience meltdown conditions, not because safety systems failed to activate, but because the fundamental assumptions about acceptable risk had been systematically embedded into every design decision. This is not an examination of a singular catastrophic event. This is an analysis of how institutional logic, regulatory frameworks, and engineering confidence created conditions where natural forces would inevitably overwhelm technological barriers. The nuclear program in Japan was built upon carefully calculated seismic assessments, sophisticated engineering models, and decades of operational experience. Each reactor was sited, designed, and licensed according to strict safety protocols that accounted for earthquake risks through probabilistic analysis and defense-in-depth strategies. Yet these same rigorous processes guaranteed that when geological reality exceeded statistical projections, the consequences would be irreversible. The sequence that followed was not the result of negligence or oversight, but the logical outcome of a system designed to operate safely within parameters that nature does not respect. The question that emerged from the wreckage was not whether the technology could have been better, but whether it should have been deployed at all in a region where the Earth itself constitutes the primary threat to nuclear containment. Japan's nuclear power program emerged in the 1950s as part of the nation's post-war reconstruction and energy independence strategy. The first commercial reactor began operation at Tokai in 1966, followed by rapid expansion that would eventually encompass 54 nuclear units across 17 sites. This expansion occurred despite Japan's location at the convergence of 4 major tectonic plates, where seismic activity represents not an occasional hazard, but a fundamental characteristic of the geological environment. The decision to pursue nuclear power in such conditions reflected a particular engineering philosophy, that sophisticated analysis and robust design could make any technology safe anywhere, given sufficient understanding of the risks involved. The foundation of this philosophy rested on seismic design standards that evolved throughout the nuclear program's development. Initially, Japanese nuclear facilities were designed according to a dual-standard approach established in the early 1980s. The S1 standard represented the largest earthquake reasonably expected during the plant's operational lifetime based on historical seismicity and known fault structures. Reactors were designed to continue operating safely during S1 level ground motion, though in practice they were programmed to shut down automatically at much lower acceleration levels. The S2 standard represented the maximum conceivable earthquake for the site, assuming a magnitude 6.5 event directly beneath the reactor. Plants were required to maintain structural integrity and achieve safe shutdown without radiation release during S2 level motion, though extensive inspection would be required before restart. This dual approach appeared to provide comprehensive protection by addressing both operational earthquakes and extreme events. The S1 standard ensured that routine seismic activity would not interrupt power generation, while the S2 standard guaranteed that even unprecedented local earthquakes could not compromise safety systems. The mathematical precision of these standards, expressed in peak ground acceleration values measured in Galileo units, created confidence that seismic risk had been properly quantified and bounded. However, this confidence rested on fundamental assumptions about the nature of seismic hazards that would prove inadequate when tested against geological reality. The S1 and S2 standards were derived from probabilistic seismic hazard assessment, PHHA, a methodology that estimates earthquake likelihood based on historical data, geological surveys, and statistical modeling. PSHA treats seismic events as random occurrences governed by probability distributions, allowing engineers to calculate the expected frequency of various ground motion levels. This approach enables rational decision-making about acceptable risk levels by providing quantitative estimates of earthquake probabilities over specified time periods. The appeal of PSHA lay in its ability to transform geological uncertainty into engineering certainty. Rather than acknowledging that earthquake prediction remains fundamentally limited by incomplete understanding of complex geological processes, PSH offered precise numerical estimates of seismic hazards that could be directly incorporated into design calculations. A 10,000-year return period event, for example, was defined as ground motion with a 0.01% annual probability of exceedance, providing apparently objective criteria for establishing design requirements. But this mathematical sophistication masked critical limitations in the underlying methodology. PSHA relies on the assumption that past seismic patterns provide reliable guidance for future earthquake occurrence, yet historical records in Japan extend back only a few centuries for detailed observations and perhaps a millennium for major events documented in written sources. Geological processes, particularly those involving major tectonic plate interactions, operate on timescales of thousands to tens of thousands of years. The statistical confidence provided by PSHA therefore rested on extrapolating limited historical data across time periods that greatly exceeded the observational record. More fundamentally, PSHA treats earthquakes as independent random events, failing to account for the coupled nature of geological processes in complex tectonic environments. The Japanese archipelago lies at the intersection of the Pacific, Philippine Sea, Eurasian, and North American plates, where the subduction of oceanic plates beneath continental margins creates conditions for megathrust earthquakes of extraordinary magnitude and duration. These events differ qualitatively from the smaller, shorter duration earthquakes that comprise most of the historical record used in PSHA calculations. The limitations of probabilistic methods became apparent in the aftermath of the 1995 Kobe earthquake, which exceeded the design basis for several facilities despite occurring in a region considered to have relatively low seismic risk. This magnitude 7.2 event prompted a comprehensive review of seismic design standards, leading to recognition that PSHA alone was insufficient for establishing safety requirements. The review concluded that deterministic approaches, considering specific fault rupture scenarios rather than statistical averages, should supplement probabilistic analysis. These insights led to a fundamental revision of Japanese seismic design standards in September 2006, when the Nuclear Safety Commission replaced the dual S1-2 system with a unified design basis ground motion (SS) standard. The new approach required facilities to withstand ground motion equivalent to a magnitude 6.7 earthquake directly beneath the reactor, representing a significant increase from the previous magnitude 6.5 requirement. Additionally, the revised standards mandated consideration of specific active faults and potential rupture scenarios, moving beyond purely statistical assessments toward more physically based earthquake characterization. The transition to the SS standard appeared to address the limitations identified in the Kobe earthquake analysis by incorporating both probabilistic and deterministic elements into seismic design. Existing facilities were required to demonstrate compliance with the new standard through comprehensive reassessment of their seismic capability. For Fukushima Daiichi, this process resulted in an upgraded design basis ground motion of 600 gal, 0.6 grams, reflecting improved understanding of local geology and more sophisticated analysis methods. However, the new standard still relied on the fundamental assumption that earthquake hazards could be bounded through engineering analysis. While the SS approach was more sophisticated than previous methods, it maintained the premise that sufficiently detailed study could identify maximum credible earthquake scenarios and design facilities to withstand them. This confidence in the ability to characterize extreme natural events represented a continuation of the engineering philosophy that had driven nuclear development in Japan from the beginning. The regulatory framework supporting this philosophy treated calculated design bases as sufficient rather than minimum requirements. Once a facility demonstrated compliance with applicable standards through detailed analysis and testing, it received authorization to operate without additional consideration of scenarios beyond the design basis. This approach reflected confidence that engineering standards, properly applied, could ensure safety under all credible conditions. The institutional structures implementing these standards further reinforced confidence in their adequacy. The Nuclear Safety Commission, Nuclear and Industrial Safety Agency, and utility companies each played specific roles in the development, review, and implementation of seismic design requirements. This distributed responsibility system created multiple checkpoints for ensuring compliance with established standards, while the technical sophistication of the organizations involved provided assurance that analyses were conducted competently. The expertise of Japanese earthquake engineering contributed significantly to this institutional confidence. Japan possessed perhaps the world's most advanced capabilities in seismic analysis and earthquake-resistant design, developed through decades of experience with frequent seismic activity. Japanese researchers had pioneered many fundamental techniques in earthquake engineering, and Japanese construction standards were widely regarded as among the most stringent globally. The nuclear program benefited directly from this expertise, incorporating the latest advances in seismic design methodology. This technical capability created a feedback loop that reinforced confidence in calculated design standards. Because Japanese engineers were demonstrably skilled at earthquake-resistant design, the standards they developed were presumed to provide adequate protection. The mathematical sophistication of PSHA and deterministic analysis methods further supported this presumption by providing quantitative justification for specific design requirements. Yet this entire edifice rested on assumptions about the nature of seismic hazards that geological science could not fully validate. While earthquake engineering had advanced tremendously in understanding structural response to ground motion, fundamental questions about maximum possible earthquake magnitudes, rupture characteristics, and recurrence intervals remained unanswered. The confidence placed in calculated design standards therefore exceeded the certainty that geological knowledge could provide. The consequences of this confidence gap would become apparent only when tested against geological reality that exceeded all previous experience and analysis. The engineering logic was internally consistent and technically sophisticated, but it was based on incomplete understanding of the geological processes that would ultimately determine whether the technology could operate safely in its chosen environment. The design philosophy that emerged from this analysis framework treated seismic hazards as engineering problems to be solved through calculation and robust construction. Natural forces were viewed as external loads to be resisted rather than fundamental constraints on technological deployment. This perspective enabled the nuclear program's expansion throughout Japan's seismically active regions by providing confidence that appropriate design could overcome any natural hazard. The institutional momentum generated by this philosophy made it increasingly difficult to question the fundamental premise that nuclear technology was compatible with extreme seismic environments. Each successful application of seismic design standards reinforced confidence in the methodology, while the absence of major accidents was interpreted as validation of the approach rather than fortunate avoidance of events beyond the design basis. When the Tohoku earthquake struck on March 11, 2011, it would test not just the technical adequacy of specific design standards, but the entire philosophical framework that assumed geological uncertainty could be bounded through engineering analysis. The magnitude 9 event that followed represented precisely the type of scenario that probabilistic methods were structurally incapable of properly characterizing, a low-probability, high-consequence event that fell far outside the historical experience base used to develop design standards. The evolution of tsunami design standards at Fukushima Daiichi reveals how institutional processes can create false confidence through incremental improvements that fail to address fundamental vulnerabilities. When the plant was originally designed in the 1960s, the design basis tsunami height was established at 3.1 meters above sea level, based primarily on assessment of the 1960 Chilean tsunami that had reached Japanese shores. This standard reflected the available methodology of the time, which relied on historical tsunami records to project future hazards. The approach appeared reasonable given the limited understanding of tsunami generation mechanisms and the absence of comprehensive geological evidence about prehistoric events. The original plant layout reflected this design basis through careful attention to elevation and protection systems. The reactor buildings were constructed approximately 10 meters above sea level, providing substantial margin above the design basis tsunami. Critical cooling systems, however, required access to seawater for heat removal and were therefore located closer to sea level. The seawater intake structures and emergency diesel generators that would prove crucial during accident conditions were positioned at approximately 4 meters above sea level, still above the design basis, but with considerably less margin than the reactor buildings themselves. This configuration reflected a fundamental tension in nuclear plant design between safety requirements and operational efficiency. Elevating all systems well above potential tsunami levels would provide maximum protection, but would greatly complicate normal operations that required reliable seawater access for cooling. The compromised position placed essential safety systems at elevations that exceeded historical tsunami records while maintaining practical access to cooling water sources. This decision embedded a latent vulnerability that would remain hidden as long as actual tsunami heights remained within the bounds of historical experience. The adequacy of tsunami protection received periodic review as understanding of tsunami hazards evolved. In 2002, the Japan Society of Civil Engineers published updated tsunami assessment guidelines that incorporated improved analysis methods and additional historical data. Application of these guidelines to Fukushima Daiichi resulted in a revised design basis tsunami height of 5.7 meters, nearly doubling the original standard. This revision prompted protective modifications including sealing of seawater pump areas to prevent flooding, demonstrating institutional responsiveness to evolving hazard understanding. The revision process appeared to validate the effectiveness of periodic safety reviews in identifying and addressing emerging risks. The fact that tsunami standards had been updated based on improved knowledge suggested that institutional mechanisms were functioning properly to incorporate new information into safety assessments. The specific modifications implemented at Fukushima Daiichi provided additional confidence that identified vulnerabilities were being systematically addressed. However, this confidence was based on the assumption that incremental improvements to historical analysis methods would eventually converge on accurate characterization of maximum credible tsunami hazards. The fundamental approach remained unchanged. Tsunami risk was assessed primarily through analysis of recorded events, with limited incorporation of geological evidence about prehistoric tsunamis that might exceed historical observations. This methodology created systematic bias toward underestimation of extreme events that had not occurred within the observational period. The limitations of historical analysis became apparent in 2008 when Tokyo Electric Power Company commissioned additional tsunami assessment studies for the Fukushima coast. These studies employed improved computer modeling techniques and incorporated geological evidence from the 1896 Meiji to Senriku tsunami, which had generated wave heights exceeding 38 meters along portions of the Japanese coast. When this historical event was used as a basis for modeling potential tsunami impacts at Fukushima Daiichi, the results indicated possible wave heights reaching 15.7 meters at the plant site. This analysis represented a fundamental challenge to the existing protection philosophy. A 15.7-meter tsunami would substantially exceed not only the original 3.1-meter design basis but also the revised 5.7-meter standard. More significantly, such an event would overtop the diesel generator buildings and potentially flood other critical safety systems, creating conditions that no existing emergency procedures had been designed to address. The implications extended beyond simple design basis exceedance to fundamental questions about plant survivability under extreme natural events. The institutional response to this analysis reveals critical weaknesses in how organizations process information that challenges established safety conclusions. Rather than immediately implementing additional protection measures or conducting comprehensive vulnerability assessments, Tokyo Electric Power Company initiated consultations with tsunami experts at the Japan Society of Civil Engineers to validate the methodology and assumptions underlying the 15.7-meter projection. This review process was still ongoing when the Tohoku earthquake occurred in March 2011. The decision to seek external validation before taking protective action reflected reasonable engineering practice for managing uncertainty in complex technical assessments. Tsunami modeling involves numerous assumptions about earthquake characteristics, seafloor displacement, wave propagation, and coastal interaction effects that can significantly influence results. The 15.7-meter projection represented a substantial increase over previous estimates and warranted careful review before driving major plant modifications. However, the extended timeline of this review process created a critical vulnerability window. The institutional mechanisms designed to ensure technical rigor in safety assessments also introduced delays that left potential vulnerabilities unaddressed. The confidence placed in existing protection measures, based on decades of successful operation and compliance with established standards, may have contributed to treating the new analysis as a technical question to be resolved rather than an urgent safety concern requiring immediate attention. This institutional dynamic reflected broader patterns in how complex organizations process challenging information. The Fukushima tsunami assessment occurred within a regulatory and corporate environment that had successfully managed nuclear operations for decades without major accidents. This track record created organizational confidence that existing safety systems and procedures were adequate for managing credible risks. Information suggesting fundamental inadequacies in protection systems therefore faced institutional resistance not through deliberate negligence, but through cognitive biases that favor continuity over disruptive change. The technical sophistication of the organizations involved reinforced these biases by providing multiple opportunities to question analyses that challenged established conclusions. The availability of expert review processes, detailed modeling capabilities, and extensive regulatory oversight created legitimate pathways for validating concerning assessments. However, these same capabilities could be used to delay action while technical debates continued, particularly when immediate responses would require substantial resource commitments or operational disruptions. The tsunami protection issue also interacted with broader organizational priorities that influenced how safety information was processed and acted upon. Nuclear power plants represent enormous capital investments that operate within competitive electricity markets. Modifications to address newly identified hazards involve significant costs and potential operational disruptions that must be balanced against uncertain benefits. While safety requirements legally take precedence over economic considerations, the practical implementation of safety improvements occurs within organizational contexts, where resource allocation decisions reflect multiple competing priorities. These institutional factors were compounded by the fundamental uncertainty inherent in tsunami hazard assessment. Unlike seismic hazards, which can be characterized through extensive geological and geophysical data, tsunami hazards depend on rare, complex events that leave limited geological records. The rarity of major tsunamis means that observational data spans only a few events over historical time periods, making statistical analysis inherently unreliable. Geological evidence from sediment deposits and other indicators can extend the time record, but interpretation of such evidence involves significant uncertainties about event characteristics and recurrence patterns. The methodological limitations of tsunami assessment created legitimate technical grounds for questioning any specific projection, including the 15.7-meter estimate for Fukushima. The modeling assumptions required to generate such projections involve numerous parameters that cannot be precisely determined from available data. Earthquake magnitude, fault rupture characteristics, seafloor displacement patterns, and wave propagation effects all influence tsunami generation and propagation in ways that are difficult to predict accurately. The complexity of these interactions provides multiple opportunities for challenging specific assessments while avoiding direct confrontation with the underlying safety implications. The organizational processing of the 2008 tsunami assessment, therefore, became entangled in technical debates about modeling methodology, rather than focused on the fundamental question of plant vulnerability to extreme events. The institutional mechanisms designed to ensure technical rigor became obstacles to timely response when technical certainty was inherently unattainable. The confidence required for organizational action exceeded the certainty that tsunami science could provide, creating conditions where critical vulnerabilities remained unaddressed while technical reviews continued. This dynamic was reinforced by the regulatory framework governing nuclear plant modifications. Changes to safety systems or operating procedures required extensive documentation, analysis, and approval processes designed to ensure that modifications actually improved safety and did not introduce new risks. While these requirements were intended to prevent hasty decisions that might compromise safety, they also created significant barriers to implementing protective measures based on uncertain threat assessments. The regulatory emphasis on technical justification meant that proposed modifications needed to be supported by comprehensive analysis demonstrating both the validity of the threat and the effectiveness of the proposed response. For the tsunami issue, this requirement created a circular problem. Implementing protection against a 15.7-meter tsunami required, accepting that such an event was credible. But the technical review process was focused on determining whether the analysis supporting this projection was valid. The human factors implications of these institutional dynamics extended beyond the specific tsunami assessment to broader patterns of organizational decision-making under uncertainty. The nuclear industry had developed sophisticated risk assessment methods and safety management systems based on the principle that technical analysis could provide reliable guidance for safety decisions. When technical analysis produced uncertain or contradictory results, these systems had limited mechanisms for proceeding with protective actions based on prudential rather than analytical considerations. The confidence placed in technical analysis reflected the generally successful track record of nuclear operations in Japan and globally. The absence of major accidents involving external hazards had validated confidence in design standards and protection systems, creating institutional momentum that favored continuity over precautionary changes. The organizational culture that emerged from this experience emphasized technical competence and regulatory compliance as the primary means of ensuring safety, leaving limited room for acknowledging fundamental uncertainties in hazard characterization. The training and professional background of nuclear industry personnel further reinforced emphasis on technical analysis over precautionary approaches. Nuclear engineers are educated in probabilistic risk assessment, deterministic analysis, and regulatory compliance methods that provide specific guidance for managing known hazards. This technical training creates professional confidence in analytical methods while providing limited preparation for managing situations where analysis cannot provide reliable guidance. The institutional structures supporting nuclear operations reflected and reinforced these professional orientations through organizational hierarchies, decision-making processes, and performance metrics that emphasized technical competence and regulatory compliance. Plant operators, maintenance personnel, and management staff were evaluated primarily on their ability to maintain safe operations according to established procedures and standards. Innovation or precautionary measures that exceeded regulatory requirements received less organizational support than demonstrated competence in managing routine operations. These organizational characteristics created systematic barriers to processing information that challenged fundamental assumptions about plant safety. The 2008 tsunami assessment represented exactly this type of challenge by suggesting that existing protection systems might be fundamentally inadequate rather than simply requiring minor adjustments. The institutional response of initiating extended technical review reflected organizational mechanisms optimized for managing incremental improvements rather than fundamental reassessments of safety assumptions. The timing of the tsunami assessment also interacted with broader industry and regulatory transitions that influenced how challenging information was processed. The Japanese nuclear industry was implementing new seismic design standards, managing plant life extension decisions, and adapting to evolving regulatory requirements that place substantial demands on organizational resources and attention. The tsunami issue became one additional technical challenge within a complex environment of ongoing safety assessments and regulatory compliance activities. The broader context of Japanese nuclear operations provided additional organizational momentum that favored continuity over disruptive changes. The nuclear program had provided reliable electricity generation for decades while maintaining strong safety records and regulatory compliance. This operational success created stakeholder confidence in existing systems and procedures, making it difficult to justify major modifications based on uncertain threat projections. The institutional confidence was reinforced by international recognition of Japanese nuclear expertise and safety practices. Japanese nuclear technology and regulatory standards were widely respected globally, providing external validation of domestic safety approaches. This international recognition created additional barriers to acknowledging fundamental inadequacies in established safety systems, as such acknowledgement would imply criticism of practices that had received widespread technical and regulatory approval. When the Tohoku earthquake and tsunami occurred on March 11, 2011, they exposed the limitations of institutional processes that had created false confidence through technical sophistication and incremental improvements. The 15.7-meter wave height that overtopped Fukushima Daiichi's defenses fell precisely within the range that the 2008 assessment had identified as credible, validating the technical analysis while demonstrating the consequences of institutional delays in implementing protective responses. At 2:46 p.m. Japan Standard Time on March 11, 2011, the Pacific Plate beneath the seafloor east of Honshu began a rupture sequence that would fundamentally challenge every assumption underlying Japan's nuclear safety framework. The initial seismic waves detected by the nationwide earthquake monitoring network indicated a major earthquake, but the full scope of what was occurring remained hidden beneath hundreds of meters of seawater. Within minutes, it became clear that this was not merely another large earthquake in Japan's seismically active environment, but a geological event of extraordinary magnitude that would exceed virtually every parameter used in nuclear plant design. The earthquake originated approximately 130 kilometers east of the Yoshika Peninsula, at a depth of 32 kilometers beneath the seafloor. The rupture began as a sudden release of tectonic stress that had been accumulating for centuries along the boundary between the Pacific Plate and the North American Plate. What distinguished this event from the thousands of smaller earthquakes that occur annually in Japanese waters was the scale of the fault rupture that followed the initial break. Rather than remaining localized to a few tens of kilometers, the rupture propagated both north and south along the subduction zone, ultimately extending approximately 500 kilometers in length and 200 kilometers in width. The magnitude of the earthquake was initially estimated at 7.9 based on the first seismic wave arrivals, a value that fell within the range of large but not unprecedented earthquakes in the region. However, as additional seismic data became available and the full extent of the rupture became apparent, the magnitude estimate was repeatedly revised upward. The final determination of magnitude 9 placed the Tohoku earthquake among the most powerful ever recorded globally, and by far the largest in Japan's documented seismic history. This magnitude revision had profound implications that extended far beyond academic seismology. The energy release in a magnitude 9 earthquake exceeds that of a magnitude 7 event by a factor of approximately 1,000, representing a fundamental difference in the geological processes involved. While magnitude 7 earthquakes involve rupture of individual fault segments over periods of tens of seconds, magnitude 9 events require rupture of multiple segments over several minutes, creating entirely different patterns of ground motion and seafloor displacement. The duration of strong ground motion at Fukushima Daiichi extended for approximately 3 to 5 minutes, far longer than the typical 30 to 60 seconds of intense shaking associated with the magnitude 6-7 earthquakes that had been used to develop seismic design standards. This extended duration placed qualitatively different demands on structural systems, which were required to maintain integrity through repeated cycles of stress reversal rather than surviving a brief period of peak acceleration. The ground motion characteristics recorded at Fukushima Daiichi revealed the limitations of peak ground acceleration as a single parameter for characterizing earthquake effects. While the maximum horizontal accelerations of approximately 550 gal at the Daiichi site and 254 gal at the Daini site remained within design tolerance levels, the prolonged duration and frequency content of the shaking differed significantly from the design basis earthquakes used in structural analysis. The cumulative energy input to structures over the extended shaking period exceeded that anticipated for design basis events, even though peak acceleration values remained within acceptable bounds. More significantly, The seafloor displacement associated with the rupture created conditions for tsunami generation that exceeded all historical precedents in the region. The earthquake involved primarily thrust faulting, with the Pacific Plate moving westward beneath the North American Plate along a fault plane that extended from near the ocean surface to depths of approximately 40 kilometers. The sudden displacement of this enormous fault area resulted in vertical seafloor movements of up to 20 meters over the rupture zone, displacing vast volumes of seawater and generating the tsunami waves that would prove far more destructive than the earthquake ground motion itself. The coupling of seismic and tsunami hazards in this single geological event exposed fundamental weaknesses in the hazard assessment methods used for nuclear plant siting and design. The probabilistic and deterministic analysis approaches that formed the basis of safety standards had treated earthquake and tsunami hazards as separate phenomena that could be analyzed independently. This approach reflected practical limitations in modeling complex coupled systems, but it failed to account for the reality that both hazards originated from the same geological processes and could therefore exceed design bases simultaneously. The immediate response of Fukushima Daiichi's safety systems demonstrated that seismic protection functioned as designed for the ground motion levels experienced. Seismic detectors throughout the plant registered accelerations exceeding preset trip levels, automatically initiating reactor shutdown procedures at 2:46 p.m. Control rods were inserted into all operating reactor cores within seconds of the initial detection, effectively terminating the nuclear fission process and beginning the transition from full power operation to safe shutdown conditions. The automatic reactor shutdown, known as SCRAM, represented the first line of defense in nuclear plant safety systems and functioned exactly as intended. The control rod insertion was completed successfully in all operating units, with reactor power levels dropping to near zero within minutes of the earthquake onset. This response validated decades of seismic design and analysis that had focused primarily on ensuring reactor shutdown capability under earthquake conditions. However, the successful reactor shutdown also initiated decay heat generation that would dominate subsequent accident progression. Although nuclear fission ceased immediately upon control rod insertion, the radioactive fission products accumulated during normal operation continued to generate heat at approximately 6 to 7% of the reactor's full power rating. This decay heat would persist for months after shutdown, gradually decreasing according to well-understood physical principles, but requiring continuous cooling to prevent fuel damage. The design philosophy underlying nuclear plant safety systems assumed that multiple independent barriers would prevent radioactive material release, even under severe accident conditions. The first barrier consisted of the ceramic fuel pellets themselves, which retain most fission products at normal operating temperatures. The second barrier was the zirconium alloy fuel cladding that surrounds the fuel pellets and provides structural support. The third barrier consisted of the reactor pressure vessel, a massive steel structure designed to contain the reactor core and primary cooling system. The fourth barrier was the containment structure, typically a reinforced concrete and steel shell designed to contain any material that might be released from the reactor vessel. This defense-in-depth approach provided confidence that multiple system failures would be required before significant radioactive release could occur. Each barrier was designed to maintain integrity under specified conditions, and the probability of simultaneous failure of multiple independent barriers was calculated to be extremely low. This probabilistic argument formed the foundation of nuclear safety analysis and regulatory approval processes. The effectiveness of this protection philosophy, however, depended critically on maintaining the engineered systems required to preserve barrier integrity. The fuel cladding barrier, in particular, required continuous cooling to prevent temperatures from reaching levels where oxidation and mechanical failure would occur. The reactor pressure vessel required inventory control to prevent core uncovery and loss of cooling geometry. The containment barrier required pressure control to prevent overpressurization from steam or gas generation. Each of these requirements could be satisfied through multiple engineered systems designed to provide redundant protection capabilities. Primary cooling systems circulated water through the reactor core during normal operation, removing decay heat and transferring it to secondary cooling loops. Emergency core cooling systems provided backup water injection and cooling capability if primary systems were lost. Reactor building cooling systems maintained containment atmosphere temperature and pressure within design limits. Emergency power systems ensured that active cooling systems could operate even during loss of external electricity supply. The robust design of these engineered safety systems had provided confidence that defense in depth could be maintained under a wide range of accident conditions. Extensive analysis and testing had demonstrated that combinations of equipment failures, human errors, and external events were extremely unlikely to simultaneously defeat multiple independent protection systems. The regulatory framework required demonstration that even severe accident scenarios would not lead to significant radioactive releases, providing quantitative confirmation of safety system adequacy. This confidence was tested immediately following the reactor shutdown when external electrical power to Fukushima Daiichi was lost due to earthquake damage to transmission lines and switching stations. The loss of external power was not unexpected, as seismic design analysis had recognized that electrical grid disruption was likely during major earthquakes. Emergency diesel generators automatically started to provide backup power for essential safety systems, maintaining reactor cooling and other critical functions. The diesel generators function normally for approximately 40 minutes, providing the electrical power needed to operate reactor coolant pumps, control systems, and instrumentation. During this period, plant operators followed established procedures for managing station blackout conditions, a scenario that had been analyzed and planned for in emergency procedures. The successful transition to emergency power demonstrated the effectiveness of redundant electrical systems designed to maintain safety functions during external power loss. The adequacy of these backup systems, however, depended on their continued operation until external power could be restored or alternative cooling methods could be implemented. The diesel generators were designed to operate for several days if necessary, providing sufficient time for utility crews to repair damaged transmission lines or implement other recovery measures. The fuel supplies for the generators were sufficient for extended operation, and additional fuel could be delivered by truck if needed. This confidence in emergency power systems reflected successful experience with previous earthquake events that had disrupted external power without compromising plant safety. Japanese nuclear plants had weathered numerous seismic events over several decades of operation, with emergency systems performing as designed and normal operations resuming once external conditions stabilized. This operational history provided validation of design assumptions and emergency planning processes. The fundamental vulnerability that would soon be exposed, however, lay not in the seismic resistance of individual components, but in the assumptions about maximum credible external events that had guided overall plant design. While individual systems had been designed to withstand severe earthquakes, the plant layout and protection systems had been optimized for the tsunami hazards characterized in design basis assessments. The location of emergency diesel generators, electrical switchgear, and other critical systems reflected confidence that the 5.7-meter design basis tsunami represented adequate protection against credible flood events. The first indication that this confidence might be misplaced came from early tsunami warnings issued by the Japan Meteorological Agency based on preliminary earthquake magnitude and location estimates. Initial warnings predicted tsunami heights of 3 to 6 meters for the Fukushima coast, values that fell within or only slightly above the design basis, but were concerning given the magnitude of the earthquake. These warnings provided approximately 1 hour of advance notice before tsunami arrival, sufficient time for plant personnel to implement emergency procedures and seek higher ground. However, the warning system itself was based on the same historical analysis methods and magnitude-height relationships that had been used to establish plant design standards. The initial tsunami height predictions reflected the best available understanding of tsunami generation and propagation processes, but they were derived from databases of previous events that did not include magnitude 9 earthquakes in the immediate region. The warning system therefore suffered from the same limitations that affected design-basis tsunami assessments, dependence on historical precedents that might not encompass the full range of possible events. As seismic analysis continued in the hour following the earthquake, magnitude estimates were revised upward, and tsunami height predictions increased accordingly. The Japan Meteorological Agency upgraded its tsunami warning to the highest level, predicting wave heights exceeding 10 meters for portions of the northeast coast. This revision indicated that the event was exceeding the parameters of typical earthquake-tsunami sequences and approaching the range of extreme events that had been considered possible but highly improbable. The plant personnel at Fukushima Daiichi were aware of the escalating tsunami warnings but faced limited options for additional protection, measures beyond those already implemented through design and procedures. The reactor buildings, control rooms, and other essential facilities were located well above the design basis tsunami height and were expected to remain functional even if lower elevation areas experienced flooding. Emergency procedures called for securing loose equipment, ensuring that important documents and supplies were moved to higher elevations, and confirming that personnel were positioned in safe locations. The confidence in structural protection was based on decades of successful operation and compliance with established design standards. The plant had been designed by experienced engineering firms using recognized analysis methods and had been reviewed extensively by regulatory authorities. The protection systems had been tested periodically and had performed satisfactorily during previous smaller tsunami events. This combination of design analysis, regulatory oversight, operational experience, and periodic testing provided multiple sources of confidence in the adequacy of protection systems. The limitations of this confidence became apparent at approximately 3:27 p.m. when the first tsunami waves began arriving at the Fukushima coast. Initial observations indicated wave heights that clearly exceeded the design basis, but remained within the range that might be manageable through emergency procedures and existing protection systems. However, the full scale of the tsunami became apparent only as successive wave crests continued to arrive, each higher than the previous waves and eventually reaching heights that exceeded all previous experience and analysis. The maximum tsunami height at Fukushima Daiichi ultimately reached approximately 15 meters above sea level, nearly 3 times the 5.7-meter design basis and remarkably close to the 15.7-meter projection from the 2008 assessment that had been under technical review. This correspondence validated the technical methodology used in the assessment while demonstrating the consequences of institutional delays in implementing protective measures based on uncertain but credible threat projections. The 15-meter tsunami overtopped the seawalls protecting critical plant areas and flooded the turbine building's housing emergency, diesel generators, electrical switchgear, and other essential equipment. The flooding occurred rapidly, with water depths reaching several meters in basement areas where critical systems were located. The combination of direct impact forces, hydrostatic pressure, and electrical system exposure to seawater caused immediate and comprehensive failure of emergency power systems that had been functioning normally since the earthquake. The transition from successful earthquake response to station blackout conditions occurred within minutes of tsunami arrival, demonstrating how rapidly engineered safety systems could be overwhelmed when design basis assumptions were exceeded. The plant status changed from a manageable emergency with multiple functional safety systems to an unprecedented situation with virtually all active safety systems disabled simultaneously. This transition marked the fundamental divergence between system design assumptions and physical reality that would drive all subsequent accident progression. The defense-in-depth philosophy had been validated under design basis conditions, but proved inadequate when multiple protection barriers were challenged simultaneously by events that exceeded the scope of design analysis. The confidence placed in calculated design standards was tested by geological processes that operated according to physical principles, rather than engineering assumptions about maximum credible events. The station blackout that began at 3:27 p.m. on March 11, 2011, initiated a sequence of physical processes that would proceed according to fundamental thermodynamic principles regardless of human intervention or engineering systems. The loss of all AC electrical power eliminated the active cooling systems that had been designed to remove decay heat from the reactor cores, but the physics of radioactive decay continued unchanged. The fission products created during normal reactor operation would continue generating heat at predictable rates, creating an inexorable demand for heat removal that could no longer be satisfied through engineered systems. At the moment of power loss, the 3 operating reactor units at Fukushima Daiichi contained approximately 1,500 megawatts of thermal energy in the form of decay heat, equivalent to roughly 6% of their normal full-power operation. This heat generation followed well-established physical laws, decreasing exponentially with time constants measured in hours and days rather than minutes. Even 24 hours after shutdown, each reactor would still generate approximately 15 megawatts of thermal energy, sufficient to boil away the water inventory in the reactor vessel within hours if no cooling was provided. The immediate consequence of losing active cooling was the termination of forced circulation that had been removing heat from the reactor cores and transferring it to the ultimate heat sink through the turbine condensers and cooling water systems. Without electrical power to operate reactor coolant pumps, heat removal became dependent on natural circulation processes driven by density differences between hot and cold water. These natural processes were far less effective than forced circulation and could function only as long as adequate water inventory remained in the reactor systems. The reactor pressure vessels in the affected units contained several hundred tons of water at the time of power loss, providing substantial thermal mass that could absorb decay heat for several hours before reaching saturation temperature. However, the closed nature of the reactor systems meant that as water heated up and converted to steam, system pressure would increase unless steam could be vented to the containment or other volumes. The reactor systems were designed to accommodate some pressure increase, but sustained heat input without heat removal would eventually exceed design pressure limits. The physics of this process were entirely predictable based on thermodynamic principles and the known characteristics of reactor systems. Heat generation rates could be calculated precisely from reactor operating history and fission product decay constants. Water inventory could be estimated from normal operating procedures and instrument readings available before power loss. Steam generation rates and pressure increase could be determined from steam tables and system volume calculations. The progression toward core damage was therefore not a matter of speculation but of straightforward engineering calculation once the boundary conditions were established. The critical parameter governing the timeline of core damage was the maintenance of adequate water level above the reactor fuel assemblies. As long as the fuel remained covered with water, heat transfer would occur efficiently through nucleate boiling, maintaining fuel temperatures well below damage thresholds even without forced circulation. However, if water level dropped sufficiently to expose fuel assemblies to steam environment, heat transfer would become much less efficient and fuel temperatures would rise rapidly toward damage levels. The reactor water level indication systems that would normally provide precise monitoring of this critical parameter were themselves dependent on electrical power and instrument air systems that had been lost in the station blackout. The few battery-powered instruments that remained functional provided only limited information about system conditions, and even these would be depleted within hours unless power could be restored. Plant operators therefore faced the unprecedented situation of managing a severe accident with minimal instrumentation to monitor critical safety parameters. The lack of reliable water level indication created fundamental uncertainty about the progression of conditions within the reactor systems. While the physics of heat generation and steam production could be calculated theoretically, the actual water level and fuel exposure could not be determined directly from available instruments. Operators were forced to infer system conditions from indirect indicators such as containment pressure and temperature, radiation readings, and observations of steam or hydrogen release from reactor buildings. This instrumentation limitation compounded the physical challenges of accident management by creating uncertainty about the effectiveness of any emergency measures that could be implemented. Without reliable level indication, operators could not determine whether emergency water injection efforts were successfully maintaining core cooling or were simply replacing water being lost through system leaks or steam venting. The feedback mechanisms essential for effective emergency response were eliminated along with the electrical systems needed for normal plant operation. The primary relief valves on each reactor system provided the only available mechanism for controlling reactor pressure once normal heat removal systems were lost. These valves were designed to automatically open when system pressure exceeded preset limits, protecting the reactor pressure vessel from overpressurization. However, the steam released through these valves carried away substantial amounts of energy and water inventory, accelerating the depletion of reactor coolant and hastening the approach toward fuel exposure conditions. The relief valve operation created a fundamental dilemma for accident management, allowing pressure to increase risked vessel failure from overpressurization, but relieving pressure accelerated coolant loss and core uncovery. This dilemma reflected the inherent limitations of reactor systems designed for normal operation with active cooling rather than extended periods of heat removal through passive mechanisms. The safety systems that functioned effectively for short-term transients became sources of additional vulnerability during prolonged station blackout conditions. The reactor containment structures surrounding each unit were designed to accommodate steam release from relief valve operation and provide an additional barrier against radioactive material release. However, the containment systems themselves were not designed for sustained steam input over periods of many hours without some mechanism for heat removal. The accumulated steam would gradually increase containment pressure and temperature, eventually approaching design limits that had been established assuming much shorter duration events. The progression toward containment failure created additional urgency for restoration of cooling or implementation of alternative heat removal methods. Containment failure would eliminate the final engineered barrier against radioactive release and could potentially damage other plant systems needed for emergency response. However, the options for containment protection were limited without electrical power for containment cooling systems or other active heat removal mechanisms. The first clear indication of core damage came from radiation monitoring systems that detected fission product release characteristic of fuel cladding failure. The zirconium alloy cladding surrounding the ceramic fuel pellets was designed to retain fission products under normal operating conditions, but would fail if temperatures exceeded approximately 1,200 degrees Celsius. Once cladding failure began, volatile fission products such as iodine and cesium would be released into the reactor coolant and eventually into the containment atmosphere. The detection of fission product release confirmed that fuel temperatures had exceeded design limits despite efforts to maintain cooling through relief valve operation and natural circulation. This confirmation eliminated any remaining uncertainty about the severity of the accident and indicated that multiple barriers in the defense in-depth protection system had been breached. The fuel pellets themselves remained largely intact at this stage, but the primary barrier against fission product release had been compromised. The progression of fuel damage followed predictable metallurgical and chemical processes once cladding failure began. The zirconium water reaction that occurred at elevated temperatures was highly exothermic, generating additional heat that accelerated fuel damage and produced hydrogen gas that accumulated in the reactor systems and containment. This reaction represented a positive feedback mechanism that made recovery increasingly difficult as fuel damage progressed. The hydrogen generation from zirconium water reaction created new hazards that had not been primary concerns during the initial accident response. Hydrogen is highly flammable and can form explosive mixtures with air under certain concentration and temperature conditions. The accumulation of hydrogen in containment or reactor building atmospheres therefore introduced combustion risks that could potentially damage systems needed for accident recovery or create additional pathways for radioactive release. The management of hydrogen hazards required venting contaminated atmospheres to prevent explosive concentrations from developing, but such venting would release radioactive materials that had accumulated in containment. This created another fundamental dilemma between protecting immediate safety of plant personnel and minimizing radiological consequences. The decision-making process was further complicated by uncertainty about hydrogen concentrations, combustion potential, and the effectiveness of available venting systems. The reactor pressure vessels themselves began experiencing thermal stress and potential structural degradation as core damage progressed and temperatures continued to rise. The massive steel vessels were designed to maintain integrity under severe pressure and temperature conditions, but prolonged exposure to extreme temperatures with minimal cooling could eventually compromise structural properties. Vessel failure would eliminate containment of damaged core materials and could lead to direct release of radioactive materials to the containment or even to the environment. The timeline for vessel failure depended on the progression of core melting and the formation of debris beds that might relocate to lower regions of the reactor vessel. If sufficient core material melted and relocated to the vessel bottom, the concentrated thermal load could exceed the vessel's ability to maintain structural integrity. This scenario, known as vessel breach, represented a fundamental failure of reactor containment that would require emergency measures to prevent direct release to the environment. The physics of core melting and relocation involved complex interactions between different materials at extreme temperatures. The ceramic uranium dioxide fuel, zirconium alloy cladding, steel structural components, and control rod materials would interact chemically and physically as temperatures rose above their respective melting points. These interactions could create debris configurations that were either more or less amenable to cooling than the original fuel assembly geometry. The formation of molten pools in the reactor vessel created potential for steam explosions if water contacted the molten material directly. Such explosions could potentially damage the reactor vessel, containment structure, or both, creating rapid pathways for radioactive release that would eliminate the remaining time available for emergency response measures. The risk of steam explosions therefore became an additional consideration in decisions about water injection and other cooling attempts. The progression beyond vessel failure would involve interaction between molten core materials and the concrete foundations supporting the reactor vessel, a process known as molten core concrete interaction. This process would generate additional heat, steam, and hydrogen while gradually eroding the final physical barriers between damaged core materials and the environment. The concrete interaction also produced carbon monoxide and other gases that could create additional combustion hazards. The ultimate concern was the potential for molten core materials to penetrate completely through containment boundaries and reach groundwater or other environmental pathways. While this scenario was considered extremely unlikely based on the thermal characteristics of concrete and the cooling that would occur as core materials spread and mixed with concrete, it represented the complete failure of all engineered barriers and the direct release of radioactive materials to the environment. Throughout this physical progression, the plant operators and emergency responders were attempting to restore some form of cooling, using whatever resources remained available. Fire trucks were mobilized to provide emergency water injection through connections that bypassed the normal reactor cooling systems. Portable generators were brought to the site to restore power to critical instrumentation and control systems. Additional personnel and equipment were dispatched from other facilities to support recovery efforts. However, these emergency measures faced fundamental limitations imposed by the physical conditions that had developed within the damaged reactor systems. The high radiation levels resulting from fission product release made direct access to many areas impossible, limiting the ability to implement certain recovery measures. The structural damage to reactor buildings from hydrogen explosions eliminated access routes and damaged systems that might otherwise have been used for emergency cooling. The emergency water injection efforts were hampered by uncertainty about flow paths within the damaged reactor systems and the effectiveness of injected water in reaching and cooling the damaged fuel. Without reliable instrumentation to monitor system conditions, operators could not determine whether injected water was actually providing core cooling or was being lost through system breaches and leakage paths created by the extreme thermal conditions. The physical processes driving accident progression continued to operate according to fundamental laws regardless of the human efforts to intervene. Heat generation from radioactive decay proceeded on its predetermined schedule, declining gradually over periods of weeks and months. Material behavior at extreme temperatures followed metallurgical principles that had been well established through previous research and analysis. The thermodynamic and chemical processes driving fuel damage, hydrogen generation, and other phenomena were governed by physical constants rather than engineering systems or human actions. This fundamental reality meant that accident progression could be halted only by addressing the underlying physical requirements for heat removal and containment of damaged materials. Temporary measures might slow the progression or limit some consequences, but permanent control required restoration of sustainable cooling mechanisms that could function reliably over the extended time periods needed for decay heat to decrease to manageable levels. The emergency response that began in the hours following the station blackout represented an unprecedented attempt to manage severe nuclear accidents using improvised methods and equipment never intended for such conditions. The loss of all engineered safety systems forced plant operators and emergency responders to devise alternative approaches to core cooling, using whatever resources could be mobilized from outside the plant. This improvised response would demonstrate both the dedication of emergency personnel and the fundamental limitations of ad hoc measures when applied to nuclear systems operating far beyond their design parameters. The first priority for emergency response was the restoration of some form of water injection to the reactor cores, as this represented the only available mechanism for removing decay heat and preventing further progression of core damage. With normal reactor cooling systems disabled by the loss of electrical power and tsunami damage, fire trucks became the primary means of delivering water to the reactor systems. These vehicles, originally intended for conventional fire suppression, were pressed into service as emergency core cooling systems for nuclear reactors containing damaged fuel and high radiation levels. The use of fire trucks for reactor cooling required extensive improvisation to create flow paths between the truck pumps and the reactor systems. Normal reactor water injection systems operated at pressures of several hundred pounds per square inch and required precise flow control to ensure proper core cooling patterns. Fire truck pumps were designed for much lower pressure operation and had limited flow control capabilities, creating immediate challenges in matching pump performance to reactor system requirements. The improvised injection systems also had to overcome the elevated pressures that had developed in the reactor systems due to steam generation from decay heat. Fire truck pumps typically operated at pressures of 100 to 200 psi, while reactor system pressures had risen to 1,000 psi or higher due to steam accumulation. Direct injection was therefore impossible until reactor pressure could be reduced through relief valve operation, but such pressure relief would result in additional coolant loss and potential containment pressure increase. The coordination between pressure relief and water injection became a critical element of emergency response strategy. Operators had to balance the need for pressure reduction to enable injection against the consequences of additional coolant and energy release into containment. This balancing act was complicated by the limited instrumentation available to monitor system conditions and the uncertainty about the actual water level and fuel damage status within the reactor cores. The water sources available for emergency injection presented additional challenges for accident management. Initially, the fire trucks used fresh water from storage tanks and other sources within the plant site. However, these sources were limited in quantity and would be exhausted within hours of continuous injection. The plant's freshwater storage capacity had been designed for normal operations and short-term emergencies, not for sustained cooling of multiple reactor cores over periods of days or weeks. The transition to seawater injection represented a fundamental departure from normal reactor operating practices and created new technical challenges for long-term accident management. Seawater contains high concentrations of dissolved salts and other impurities that could cause corrosion, precipitation, and other chemical reactions within reactor systems. While seawater injection was recognized as necessary to maintain some form of cooling, it would virtually guarantee that the affected reactor units could never return to service due to extensive contamination and corrosion of internal components. The decision to use seawater injection reflected the transformation of accident management objectives from preserving plant assets to preventing radiological releases that could threaten public health and safety. This decision represented an acknowledgement that the affected reactor units were effectively lost, and that emergency efforts should focus on minimizing the consequences of their failure, rather than attempting restoration to normal operation. The chemical consequences of seawater injection began immediately upon contact with the high-temperature reactor systems. The dissolved salts in seawater would precipitate as solid deposits when exposed to the elevated temperatures present in damaged reactor cores, potentially creating blockages that could interfere with coolant flow patterns. These deposits could also create local hotspots where heat transfer was impeded, leading to further fuel damage even with continued water injection. The interaction between seawater and the zirconium cladding and other reactor materials accelerated corrosion processes that were normally negligible during reactor operation. The high-temperature, high-radiation environment within the damaged cores created conditions where chemical reactions proceeded at rates far exceeding normal industrial processes. These reactions consumed injected water through chemical decomposition and generated additional hydrogen gas that accumulated in reactor and containment systems. The effectiveness of emergency water injection was inherently uncertain due to the limited instrumentation available to monitor flow paths and cooling performance within the damaged reactor systems. Operators could measure the flow rates being delivered by fire truck pumps and monitor containment conditions that might indicate steam production, but direct measurement of reactor water level and fuel temperature was not possible with the available emergency power supplies and instrument systems. This instrumentation limitation created fundamental uncertainty about whether emergency cooling efforts were actually reaching and cooling the damaged fuel or were being lost through system leaks and breach pathways created by the extreme thermal conditions. Water injected into reactor systems that contained breached fuel assemblies and pressure vessel penetrations might not remain in contact with the fuel long enough to provide effective cooling, instead flowing out through damage-created openings and accumulating in containment or reactor building basement areas. The accumulation of contaminated water in plant buildings created secondary challenges for emergency response operations. As water injection continued over periods of days, hundreds of thousands of gallons of highly radioactive water accumulated in basement areas of reactor and turbine buildings. This water contained dissolved and suspended radioactive materials from contact with damaged fuel, and became a significant radiation source that limited personnel access to areas needed for emergency response activities. The management of contaminated water required improvised storage and treatment systems that had never been planned or designed for such applications. Temporary storage tanks were brought to the site to contain water that was removed from building basements, but the volume of water generated by continuous injection quickly exceeded available storage capacity. Treatment systems were needed to remove radioactive materials before water could be released to the environment, but such systems were not readily available and would require extensive time to design, procure, and install. The contaminated water issue demonstrated how emergency response measures intended to address immediate safety concerns could create long-term environmental and operational challenges. The success of water injection in preventing immediate core damage progression was achieved at the cost of creating massive volumes of highly contaminated water that would require management for many years. This trade-off reflected the prioritization of immediate safety over long-term consequences, but it also illustrated the interconnected nature of nuclear accident management challenges. The hydrogen generation from continued core damage and seawater injection created explosion hazards that threatened the integrity of reactor buildings and the safety of emergency response personnel. Hydrogen gas is lighter than air and tends to accumulate in upper portions of buildings, where it can form explosive mixtures if concentrations reach 4 to 15 in the presence of air. The reactor buildings at Fukushima Daiichi were not designed as containment structures and lacked the hydrogen management systems that might have prevented explosive concentrations from developing. The first hydrogen explosion occurred at Unit 1 on March 12, approximately 24 hours after the initial station blackout. The explosion destroyed the upper portion of the reactor building and created a debris field that complicated emergency response operations. While the explosion occurred outside the primary containment and did not directly breach the reactor pressure vessel, it eliminated access routes and damaged systems that might have been useful for emergency cooling efforts. The Unit 1 explosion demonstrated that hydrogen hazards were not merely theoretical concerns, but immediate threats that could disrupt emergency response operations and create additional pathways for radioactive release. The explosion scattered radioactive debris over a wide area around the reactor building and created airborne radioactive materials that increased radiation exposure risks for emergency personnel. These consequences forced temporary evacuation of some emergency response teams and reduced the workforce available for critical accident management activities. Similar hydrogen explosions occurred at Units 3 and 4 over the following days, each causing extensive damage to reactor building structures and creating additional complications for emergency response. The Unit 4 explosion was particularly concerning because it occurred in a building containing spent fuel pools that had been drained of cooling water due to the station blackout. The explosion raised concerns about potential damage to the spent fuel assemblies and additional radioactive release pathways. The spent fuel pool cooling challenge represented a secondary crisis that developed in parallel with the reactor core cooling efforts. The pools contained hundreds of spent fuel assemblies that continued to generate decay heat and required continuous cooling to prevent fuel damage. The loss of electrical power eliminated normal pool cooling systems, and the water inventory in the pools would gradually evaporate due to decay heat if not replenished. The spent fuel pools were located in the upper portions of reactor buildings and were accessible only through overhead cranes and other systems that had been damaged or rendered inoperable by the station blackout and subsequent explosions. Emergency water injection into the pools required helicopter drops or long-range water cannons that could deliver water from safe distances, but these methods were far less precise and reliable than normal cooling systems. The management of multiple simultaneous crises stretched emergency response resources and complicated decision-making processes. Personnel and equipment had to be allocated among reactor core cooling, containment venting, spent fuel pool cooling, contaminated water management, and site access maintenance. Each of these challenges required specialized expertise and equipment, and the limited resources available had to be prioritized based on immediate safety requirements rather than optimal technical solutions. The communication and coordination challenges were compounded by the damage to normal communication systems and the hazardous conditions that limited personnel access to many areas of the plant. Emergency response teams had to work with incomplete information about plant conditions and limited ability to verify the effectiveness of their actions. Decision-making processes that normally relied on detailed technical analysis and systematic evaluation had to be compressed into rapid judgments based on limited data and uncertain outcomes. The external support provided by government agencies, other utilities, and international organizations gradually improved the resources available for emergency response. But the mobilization of such support required time that was not available during the initial crisis period. The most critical decisions about emergency cooling methods, containment venting, and personnel evacuation had to be made during the first hours after the accident, using only the resources immediately available at the plant site. The psychological stress on emergency response personnel added another dimension to the accident management challenge. Plant operators and emergency responders were working under extremely hazardous conditions with uncertain effectiveness of their actions and limited information about the consequences of different response strategies. Many personnel were also concerned about the safety of their own families in the surrounding communities that were being evacuated due to radiological releases. The progressive degradation of plant conditions despite emergency response efforts created increasing pressure for more dramatic interventions that carried higher risks but might provide more effective accident control. The consideration of seawater injection had represented one such escalation, accepting permanent plant damage to maintain some form of cooling. Further escalations might include more extensive containment venting with higher radiological releases, or even flooding of entire reactor buildings to ensure submersion of damaged cores regardless of system integrity. The effectiveness of emergency response measures could be evaluated only indirectly through observations of containment pressure, radiation levels, and visual indicators such as steam releases and building damage. Direct measurement of core conditions, fuel damage extent, and cooling effectiveness was not possible with the instrumentation systems available during emergency conditions. The success or failure of emergency cooling efforts therefore remained uncertain even as they continued over periods of days and weeks. The transition from emergency response to long-term stabilization required different technical approaches and resource commitments than the immediate crisis management. While fire trucks and other improvised systems might provide sufficient cooling to prevent immediate fuel damage progression, sustainable accident management would require more robust and reliable cooling systems that could operate continuously for months or years while decay heat gradually decreased to manageable levels. The long-term cooling challenge was complicated by the extensive contamination of reactor systems with seawater and radioactive materials, which would interfere with the operation of any permanent cooling systems that might be installed. The chemical environment within the damaged reactor cores had been fundamentally altered by the accident progression and emergency response measures, creating conditions that no permanent systems had been designed to accommodate. The physical evidence that emerged from Fukushima Daiichi in the months and years following the accident provided unprecedented insights into the behavior of nuclear reactor systems under extreme conditions that had never been directly observed before. The forensic investigation required the development of entirely new methods for examining highly radioactive materials and severely damaged reactor components, using robotic systems, remote sensing technologies, and computer modeling to reconstruct what had occurred within the reactor vessels during the most severe phases of the accident. The first comprehensive assessments of core damage were conducted using industrial endoscopes inserted through existing penetrations in the reactor pressure vessels. These investigations, beginning approximately 1 year after the accident, revealed extensive fuel damage and debris formation that confirmed theoretical predictions about core melting and relocation processes. The images obtained showed that significant portions of the reactor cores had indeed melted and relocated to lower regions of the pressure vessels, creating debris beds with geometries that bore little resemblance to the original fuel assembly configurations. The endoscopic examinations of Unit 1 revealed that water levels within the reactor vessel had stabilized at approximately 1 meter above the vessel bottom, far below the normal water level that would have covered the original fuel assemblies. This finding confirmed that traditional reactor water level instruments would have been completely inadequate for monitoring conditions during the severe accident, as they were designed to measure level variations within the normal operating range rather than the extreme low-level conditions that developed after core relocation. More significantly, the low water levels indicated that the emergency water injection efforts, while successful in achieving some degree of cooling, had not restored normal core cooling geometry. The debris beds formed by melted fuel and structural materials were apparently being cooled by a combination of water contact at their lower surfaces and steam cooling where debris extended above the water level. This cooling configuration had never been analyzed in detail for reactor safety applications and represented entirely new thermal hydraulic conditions. The examination of Unit 2 provided evidence of different core damage progression patterns despite similar initial conditions and emergency response measures. The endoscopic investigations showed less extensive fuel relocation, but more severe damage to internal reactor structures, suggesting that the details of accident progression were highly sensitive to specific conditions that could not be controlled or predicted accurately during emergency response. The variability in damage patterns among the 3 units demonstrated that even apparently similar reactor systems could behave very differently under extreme conditions. The forensic evidence from Unit 3 was more difficult to obtain due to higher radiation levels and more extensive structural damage from the hydrogen explosion. But the available data suggested core damage patterns that were intermediate between Units 1 and 2. The variation in damage patterns among the 3 units provided valuable insights into the range of possible severe accident progressions and the limitations of theoretical models that had been developed based on limited experimental data and computer simulations. Perhaps the most significant forensic finding was the confirmation that reactor pressure vessel failure had not occurred in any of the 3 units, despite the extensive core damage and melting that had taken place. The massive steel pressure vessels had maintained their structural integrity even when subjected to molten core debris at temperatures exceeding 2,000 degrees Celsius for extended periods. This finding contradicted some theoretical predictions that had suggested vessel failure was likely under such conditions. The preservation of pressure vessel integrity had profound implications for understanding the effectiveness of emergency response measures and the ultimate consequences of the accident. If the vessels had failed completely, the molten core materials would have been released directly into the containment structures, creating much more severe contamination and potentially leading to containment failure as well. The successful containment of damaged core materials within the pressure vessels provided the final barrier that prevented even more catastrophic releases. However, the forensic evidence also revealed that the pressure vessels had not emerged unscathed from their exposure to molten core materials. Detailed examinations using muon tomography and other advanced diagnostic techniques indicated that significant erosion and thinning had occurred in the vessel bottom areas where molten debris had accumulated. While complete vessel failure had not occurred, the structural margins that prevented such failure were much smaller than originally anticipated. The containment structures surrounding the reactor systems had also maintained their primary containment function despite being subjected to pressures, temperatures, and chemical conditions far beyond their design parameters. The concrete and steel containment shells had experienced some cracking and seal degradation that allowed controlled releases of contaminated gases, but gross containment failure that would have led to uncontrolled massive releases had not occurred. The examination of containment conditions revealed extensive contamination with fission products that had been released from the damaged fuel, confirming that the fuel cladding barrier had been extensively compromised as predicted by early radiation monitoring data. However, the containment of these materials within the containment structures demonstrated that this engineered barrier had performed its intended function of preventing direct release to the environment, even under conditions that greatly exceeded design assumptions. The analysis of contamination patterns within the reactor buildings and surrounding areas provided detailed information about the pathways and timing of radioactive releases that had occurred during the accident. The predominant releases had occurred through planned containment venting operations intended to prevent containment overpressurization, rather than through uncontrolled breach of containment boundaries. This finding validated the emergency decision-making that had prioritized containment protection even at the cost of controlled radiological releases. The environmental monitoring data collected during and after the accident provided comprehensive documentation of the radiological consequences that resulted from the containment venting and other release pathways. The radiation exposure levels measured in surrounding communities confirmed that early evacuation decisions had been appropriate and had successfully prevented radiation doses that could have caused immediate health effects in the general population. The long-term environmental contamination patterns revealed the complex transport and deposition processes that determine the geographic distribution of radiological impacts. The contamination plumes extended primarily to the northwest of the plant site, reflecting wind patterns that prevailed during the period of major releases. The contaminated areas included agricultural regions that would require long-term monitoring and possible restrictions on food production, creating economic and social impacts that extended far beyond the immediate plant vicinity. The comparison of measured environmental impacts with pre-accident predictions revealed both the strengths and limitations of radiological consequence modeling methods. The overall magnitude of releases fell within the range of severe accident scenarios that had been analyzed for regulatory purposes, confirming that the basic physics of fission product transport were reasonably well understood. However, the detailed timing and spatial distribution of contamination showed significant variations from modeled predictions, reflecting the complexity of atmospheric transport processes and the site-specific conditions that influenced release patterns. The economic analysis of accident consequences provided quantitative assessment of the costs associated with severe nuclear accidents that had previously been estimated only theoretically. The direct costs of emergency response, plant stabilization, contaminated water treatment, and eventual decommissioning were estimated to exceed $100 billion over the projected duration of cleanup activities. These costs far exceeded the economic benefits that the affected plants had provided during their operating lifetimes, fundamentally altering the cost-benefit calculations used to justify nuclear power development. The social and psychological impacts of the accident extended well beyond the immediate radiological consequences and created long-term effects on communities throughout the region. The evacuation of approximately 150,000 people from areas surrounding the plant created displacement and disruption that persisted for years after the accident. Many evacuees were unable to return to their homes due to continued contamination concerns, creating permanent changes to rural communities that had existed for generations. The investigation of institutional decision-making during the accident revealed both effective emergency response capabilities and significant organizational weaknesses that had contributed to accident progression. The plant operators had demonstrated remarkable dedication and technical competence under extremely challenging conditions, implementing improvised emergency measures that prevented even more severe consequences. However, the organizational and regulatory systems that were supposed to prevent such accidents had failed to adequately address known vulnerabilities. The regulatory analysis identified multiple opportunities where different institutional decisions could have prevented or mitigated the accident consequences. The 2008 tsunami assessment that had predicted wave heights similar to those actually experienced had been subjected to extended technical review that delayed implementation of protective measures. Emergency preparedness plans had not adequately addressed extended station blackout conditions or multi-unit accidents, leaving responders without clear guidance for managing the unprecedented conditions that developed. The technical review of plant design and siting decisions revealed systematic weaknesses in the hazard assessment methods used for nuclear facilities. The probabilistic approaches that formed the foundation of seismic and tsunami analysis had proven inadequate for characterizing low-probability, high-consequence events that fell outside historical experience. The confidence placed in calculated design bases had not been supported by sufficient acknowledgement of the uncertainties inherent in natural hazard assessment. The international nuclear community responded to the Fukushima accident by implementing comprehensive reviews of severe accident management capabilities and natural hazard protection at nuclear facilities worldwide. These reviews identified similar vulnerabilities at many facilities and led to requirements for enhanced emergency equipment, improved severe accident procedures, and more robust protection against extreme natural events. The regulatory changes represented the most significant modifications to nuclear safety requirements since the 3 Mile Island accident 3 decades earlier. The development of new severe accident management technologies was accelerated by the lessons learned from Fukushima emergency response operations. Portable emergency equipment designed specifically for nuclear applications was developed to replace the improvised fire trucks and other equipment that had been used during the accident. Emergency response centers were hardened against natural disasters and equipped with enhanced communication systems to maintain coordination during extreme events. The advancement of severe accident analysis capabilities incorporated the detailed forensic evidence from Fukushima to improve computer models and experimental programs used for nuclear safety research. The actual behavior of reactor systems under extreme conditions provided validation data for theoretical models and identified areas where additional research was needed to understand complex physical processes. This improved understanding enhanced the technical basis for severe accident management and regulatory decision-making. The fundamental questions raised by the Fukushima accident extended beyond technical improvements to the basic assumptions underlying nuclear power development in regions subject to extreme natural hazards. The demonstration that sophisticated engineering analysis and robust safety systems could be overwhelmed by natural events that exceeded design assumptions challenged the confidence that had supported nuclear expansion in seismically active regions worldwide. The philosophical implications of the accident reached to the core assumptions about technological risk management and the relationship between scientific uncertainty and engineering confidence. The Fukushima accident had occurred not because of failures in scientific understanding or engineering competence, but because institutional systems had systematically excluded credible but low-probability scenarios from mandatory safety analysis. The accident demonstrated that technical sophistication could become a source of overconfidence when it created illusions of certainty about fundamentally uncertain natural processes. The long-term legacy of the Fukushima accident would be determined not only by its immediate radiological and economic consequences, but by its influence on societal attitudes toward technological risk and the institutional mechanisms used to manage complex technological systems. The accident provided definitive evidence that low-probability, high-consequence events could not be dismissed as incredible simply because they had not been observed previously or because their probability appeared negligible in statistical analysis. The forensic reconstruction of the Fukushima accident ultimately revealed that the sequence of failures was not the result of inadequate technology or incompetent personnel, but of systematic institutional blindness to scenarios that were technically credible but statistically improbable. The sophisticated analysis methods and regulatory oversight systems that had provided confidence in nuclear safety had created false certainty about the adequacy of protection against extreme natural events. The accident demonstrated that geological and meteorological processes operate according to physical principles that do not respect human calculations about acceptable risk levels.